Okay, so there's a quick video while I'm ready to go home right here on a Monday afternoon. We're in class 8. We are entering Bernoulli and energy equations, and I believe this is chapter 5 that we've just started. And this is the big one, Bernoulli. Boom! Daniel Bernoulli, and he came up with this in 1738. Came up with this equation. Not necessarily exactly looks like this, but something along those lines. But this is the big idea, that we have the pressure plus 1/2 the density times velocity squared plus gamma, which is the specific weight, times the height, the vertical distance, is going to be equal to is going to be constant along a streamline. This equation's more than it appears. It really does the essence that we want to try to do in fluid mechanics, which is to tie pressure and flow together. It's also an energy balance. It's a whole lot of things. But it's probably the most used and abused equation in fluid mechanics. So Daniel Bernoulli published his masterpiece in 1738, and actually his father, who was jealous, tried to plagiarize him. It really explained how speed of a fluid affects the pressure, or vice versa as well. And the Bernoulli effect explains really how airplanes generate lift. It's a really important relationship. I think I have another thing on here. I don't know. Okay, well, just that it was some groundbreaking work right there. And I took this off of famousscientist.org, and so give them attribution where it's due. Here's my cartoon that represents a really common application of Bernoulli, and that's a Venturi tube, where we change from one size of a pipe down to a smaller one and then back up again. And then we go into maybe a larger tank where we slow down. So we have this like pressure differences in each of these spots. Well, if you could see along a streamline, if we had a common streamline along here, pressure and velocity will, there'll be a trade-off, right? So a high pressure might be a low velocity, but a high velocity might be a low pressure. And you can think of these as different kinds of pressure. We will in later classes. But the pressure gauge is a type of measurement that only measures the static pressure. So you can see it actually drops down. And if you drop down low enough in a liquid, it could change phase. So water will turn into itty bitty steam bubbles. We call that cavitation. So sort of the funny thing here is wetted turns into vapes just for a moment. But then he recovered and turned back into water. So any of these three spots will be equal to each other as long as it's along a streamline. This is a very long and tedious derivation, but it's worth looking at and noticing that we could get from Newton's second law to Bernoulli. They're right tied to each other. So we can say the net pressure force and the gravitational force is going to equal to the particle mass times the particle acceleration. So F equals ma. But we need to start, we have to make some limiting things on it in order to get there. So first off, we're talking about steady flow, which doesn't mean that it's not accelerating. It just means that if you took a snapshot and it came back a little time later, that snapshot would have the same things happening to it, right? They'd be different particles that were accelerating, but it would be a steady condition. And those streamlines that we'd previously defined, those are really going to be the coordinate systems. We're going to use those to generate a coordinate system, and we'll even call them the S coordinate and the N coordinate. So the S is going to be along a streamline, where the N is going to be normal to it. And the normal one will have some curvature, and we'll know that we'll have like a centrifugal acceleration as part of that. But we're mostly focused on the streamlines as being a coordinate system that we're going to use. And based on the geometry of the streamlines, there's a few things we want to observe. We can see that the acceleration along the streamline or normal to it are equal to 0 if they're parallel. if they start to converge, the streamlines get closer together, that implies that there's going to be acceleration along the streamline. And if they were parallel and curving, well, they would definitely the normal acceleration would be greater than 0. And likewise, if they're curving but then they're merging at the same time, then both the acceleration along the streamline and normal to it are greater than 0. So that's like this idea of the streamline coordinate system, and we take a look at a free body diagram of a chunk, right? And so just to kind of a little navigation here, we set up our unit vectors S and N, and we look at the forces on this chunk. Now this short chunk is not an infinitesimal chunk, it's just a really small chunk. And this is trying to be inclusive of all the different forces that are acting on there. We see that it's in an angle, so that the weight has both an S component and an N component. And we can see that it's different by theta. We can also see that there's a pressure difference on the left and a pressure difference on the right end of this piece. And the reason why we don't have an infinitesimal piece is because if it was an infinitesimal piece, the pressure would be the same on all sides. But we have just a big enough chunk, so that's where we're using these little del things instead of using lowercase d's to say, well, it's a little bigger than just being an infinitesimal thing. And so the pressure on the left-hand side is different from the pressure on the right-hand side. So there is a pressure gradient across the length of this thing. It happens on the top and the bottom of it as well, but we really don't care so much about that at the time. We really just worry about along a streamline. So we could break these apart and look at those individual forces and apply them and the acceleration and the mass to try to see how they combine together to generate Bernoulli. I don't know, it didn't go very well in class, so maybe this time through everything is going to work out better. Maybe? I don't know. We'll see. But I think I put a lot of people to sleep while I was doing this, so let's try to avoid that this time. Try to be smooth. Now, the acceleration we're going to use is, instead of being the time-based acceleration, we're going to use that alternate term for acceleration, where the velocity times the change in velocity over the change in position. So that's our go-to acceleration right here. So we take a look at what are the forces that are acting on this. Well, we have pressure forces and we have weight forces. So the pressure forces we'll start out with, and they're really going to be. So I'm going to say, how do I want to write this? I want to go. The forces due to F, the pressure forces along the streamline right here. Those are incremental forces that are happening onto this body are going to be this force and that force. But when you end up combining them, they really just become what happens, the difference that are happening along this length right here times the volume here. Okay. Let me just pause just for a second. I just want to take a look at something. I don't like the phraseology of that. Okay, so I erased that dv right here. Really, what we're gonna have that ds right there, and this is just a statement. What's the pressure acting onto this face right here? There's a pressure difference that's going across these two right here, and what are they going to be? Well, let's take a pressure gradient per displacement and multiply it by this s. So those two would cancel each other out. It's going across this distance that we have a pressure gradient. But that's going to be acting along the face, which is dn and del n and del y, but that ends up being the volume. Right, that right there is a volume. So that statement I had previously, it is correct. But that's why, right there. I didn't like the jump that it had right there. Okay, and then we also have weight, and this is only going to be a portion of the weight, right? We only care about the weight in the s direction, and you notice it's going to be pointing in the negative s direction right here. I should also point out that we're going to assume the pressure gradient is increasing in the S direction. That's why this is negative, right? Because it's actually going to be a larger pressure on this side than that, so it's pointing in the negative S direction. So maybe the incremental weight of this thing is going to be a, let's see, I'm going to write this right down. I'm going to start looking back at my notes. Whoops. So we had negative, the small chunk of weight times the sine of theta, right? Which could also be found as a negative gamma times incremental volume, right? A small piece of volume, but also sine of theta, right? And that sine is because this thing, we've positioned this generic chunk at an angle. So we need to do a couple things. No, I think we can combine with our, where did I put it? Where did I put the mass? I guess it's supposed to be at the top somewhere, where I was supposed to write that the MA of the sum of the forces equals mass times acceleration. These are in the S direction, and that's in the S direction, and the acceleration in the S direction is written right over there. So we could also say it's going to be the mass times the volume. So I think I can write that in here. The gamma times the sine of theta, I'm doing the weight first, times the incremental volume minus the del P del S times the incremental volume. And that's going to be equal to rho times, I'll put my little incremental volume here. That's supposed to be incremental volume, not a D, but not a D, but a del. And here's my incremental volume. So there's mass right there. That's the mass of the chunk. And then times V del S. Well, we had a nice little thing where we can get rid of all of these volumes. That's good. Now we need to, so I divided by this, and I need to manipulate a little bit. First off, I can say that the sine of theta is going to be equal to dz. I think we're calling z. Sure. Yeah, okay, so it's dz. Z is in the vertical axis, right? The axis out of the page is y, right here. So d z ds right in there. And then we also have, we could also say a simplifying thing. We could say that the velocity, this right here, dv ds, we could actually do a quick little thing and say, well, how did we get to dv ds? Let's say that we have 1/2, so we kind of did like a little quasi-integration thing going right there, right? Where that's good. That should be in parentheses. I think we could buy that, right? And then the last thing we did is we said dp was equal to del p del s ds. So I think so. And then we could divide that out in here. So we're merging all of these things together. And we get negative gamma dz ds, right? Because we replaced that right into there, that sign. And minus dp ds. And then it had it equal to rho 1/2 dv squared ds. And we just say all those ds's kind of go away. So rearranging yet again, and then bringing this over to the other side, we could say dp plus 1/2 rho dv squared plus gamma dz is equal to 0. And then let's just integrate that thing. Integrate all of them. And what we're left to find is that get P plus 1/2 rho V squared plus gamma Z is equal to a constant. And as long as this was compressible, we were able to do that, right? So it had to be, excuse me, as long as this was incompressible, we were able to integrate. Because otherwise, that density would have changed, and that gamma would have changed. So our one amongst our very, very important equations, and this is where I meant to write that down here, right? So that was where that belonged onto the page. That this is the Bernoulli equation. And it has a bunch of assumptions. Like, first off, no viscous forces. That's because up here, those viscous forces, that force could have been in the S direction, but we had to assume that it was zero. So we were another way of saying no viscous forces is inviscid. Steady flow. So this could be, we couldn't be varying, time varying in here. We really just varying with along position, which is really what we're saying, that the acceleration is varying with position and not necessarily varying with time. It's along a streamline. That's an important thing, right? So if you're jumping from streamline to streamline, things are going to be different. And then lastly, it had incompressible. So we need to obey all of these things. There's like some others that we might want to also consider. We want to make sure that... let's see, I think I have it in the slides that from Sengel. So here's some other things in the Bernoulli equation section. And here's the acceleration. They're doing a very similar to what we've just done. So please look in the book and read the Sengel book. As long I'm trying to also act as be a helper here, but take a look at their derivation. They're doing something very, very similar, just changing a few things up. And I think there was somewhere in here where it's telling you not to break the rules. No, okay, I lost it. They in their rules they had like instead of just the 4, I think 4 is enough to memorize. I think they had 6 in theirs. I can't remember. One of them is the heat transfer. Another, let's see. Let me see if I get to them. Okay, so no shaft work. Yeah, that's important. Okay, so there's like not a pump going on in here, that or a turbine that would add or take away energy from the system. And we're going to see these Bernoulli equations re-derived by way of using energy, because this really is an energy balance. So we'll take a look at that at another date.